અમે આશા રાખીએ છીએ કે આપ કુશળ હતો કુશળ છીએ અહીંથી લે લેજો કીધું ગત શૈક્ષણિક વર્ષ 24-25 માટે સુધારેલી ફીનું ફાઇનલ માળખું સરકાર શ્રી તરફથી આવી છે અને ગત વર્ષ ધોરણ 1 ના વિદ્યાર્થીઓ માટે ફી અમારા દ્વારા લીધેલ ફી કરતા ઓછી છે તો તે મુજબ અમે આગામી 5 દિવસમાં દરેક બાળકને વધારાની ફીની રકમ પરત કરવાની ફી રિફંડ તે જ ખાતામાં જમા કરવામાં આવશે જે ખાતા નંબર તમે અમને આપશો તો આ પ્રક્રિયા કરવા માટે અમે એક ખાસ મીટિંગ પ્રિન્સિપાલ અને વાલીઓની બોલાવી છે જેમાં બધી રિફંડની માહિતી આપવામાં આવશે મીટિંગની 20/1/2024 મંગળવારે બપોરે 2 વાગ્યે રાખવામાં આવેલ છે વાલીશ્રીઓને વિનંતી કે બપોરના 1:30 વાગ્યા સુધીમાં આવી જાય જેથી અમે 2 વાગ્યે મીટિંગ શરૂ કરી શકીએ વાલીશ્રીએ પેન સાથે લાવવાની રહેશે માતા અથવા પિતા એક વાલીનું આવવું ફરજિયાત છે આપનો સહકાર અપેક્ષા છે રાજકોટ જિલ્લા શિક્ષણ અધિકારી જિલ્લા પ્રાથમિક શિક્ષણ અધિકારી આ બધી જગ્યાએ એને
લઈ જાવ આવી ટાઈટ નો કદાચ અમે બે આવ્યા તો દેવમને તો બહુ ઓલું નથી મારી ઈચ્છા કેમ કે ટાઈટ બહુ છે ને નહીં ને વળી હા મેં તો જોયું તું વેધર 2 દિવસનું
આપણા પૈસા પણ પાછા આપે વ્યાજ
હા અને પાછા થોડુંક જો શરદી જેવું છે એટલે વળી જોઈએ તોય હજી એમ તો એમ કીધું છે કે 2 જણા આવજો આમ કેવું કે એકદમ આમ ભાર દઈને નથી કીધું ને એકદમ આમ કીધું છે ભાર દઈને નથી કીધું એના જેવું ગોપીનો ફોન આવ્યો હતો ફુવાનો આવ્યો ફુવા 2 હતા અને ગોપીનો તો અલગથી જ ફોન આવ્યો હતો કે આવજો એવું કેવા તમારા આમંત્રણની જરૂર હોય પપ્પા કન્ફ્યુઝન હોય એટલે પપ્પા તમને પૂછતા હોય કે તમે કેવો તો અમે આવીએ બાકી કઈ એવું ન હોય
Very good evening to all. Is there anyone? Hello?
Yeah, good evening, sir.
Very good evening. Thank you.
Professor Naveen Seth here joined. थोड़ा क्या sir, Professor Naveen Seth?
Welcome, sir.
Yes, I joined. Okay.
Yes, sir. Welcome, sir. We will start soon. Just give us 2 minutes.
Okay, no problem. Yeah.
Welcome, sir. Good evening, sir.
Yes. Thank you.
Am I
In
audible?
short time. Yes, ma'am.
Yes, is my voice
Yes,
audible?
ma'am, you are audible. Yes,
Yes,
you are
ma'am.
audible.
Okay. Very quickly, we are beginning our session now. And as per the tradition of our institute, we'll start that with the three Omkars. Everyone, can we have the deep breath? And let's have an Omkar. Yeah. Om. Today, first of all, I would welcome our trustee, Dr. Navin Sheth, sir. And before we can start this FDP, it's a good day to start because it's the auspicious days of Mahanavaratri, as we all are knowing. So let us start enchanting about the goddess that Yadevi Sarva Bhuteshu Vidya Rupena Sanstita. Namastasye, 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 Namo Nama. On behalf of our department, our head of the department, Dr. Paresh Dholakia sir, is with us, and I would request Honorable Dholakia sir to give his welcome speech and also enlighten us about the FTP and the department. Over to you, Dholakia sir.
So, thank you, Sneha ma'am. I welcome all the participants from the entire country and few participants maybe from the international side. Our few speakers are also from the international side. First of all, I overview the V.V.P. Engineering College, who is the host here. I welcome our trustee, Sri Navin Bhai Seth, sir, and I'm giving you the overview of the V.V.P. Engineering College. Am I audible, everyone?
Yes, sir, you are
Yes, sir.
audible.
Okay.
Very,
Thank you. Thank
very
you.
clearly.
V.V.P. Engineering College is active since 1996. It's the first self-financed engineering college in the Saurashtra Kutch region. It operates under the motto Rastrai Swaha Idam Namama. Everything of mine is offered to my nation. It is established by Vyavasai Vidya Pratishthan V.V.P. Trust in 1996 with significant financial support from Rajkot Nagrik Sahkari Bank. To meet the higher education need of Saurashtra and Kutch, this college is established. Our current trustees include Sri Kausik Bhai Sukla, Sri Harshal Bhai Maniyar, Dr. Sanjeev Bhai Oza, Dr. Narendra Bhai Dave, and Dr. Navin Bhai Seth. Dr. Navin Bhai Seth is present here. He is a former Vice Chancellor of Gujarat Technological University, GTU. About the college departments, we have several engineering branches in mechanical engineering, chemical engineering, electrical engineering, civil engineering, computer engineering, information technology, electronics and communication, biotechnology. We are also conducting major and minor courses in Internet of Things, 3D printing, industrial process safety, computer-aided civil engineering process, electrical and computer. Last year, we have started diploma engineering in mechanical, electrical, chemical, civil, computer, and IT engineering. Awards and recognition about the college. Institute got the IST Best Student Chapter Award in 2006, 2008, 2009, and 2013. We got National Award for Best Engineering College, awarded by Bharati Vidya Bhavan in 2014. GTU Certificate of Appreciation for Research Contribution in 2016. I2I, that is the Innovative to Impact Award from GTU Innovation Council in 2023. Devang Mehta IT Award received in 2022. Mental Health and Wellness rank in the Gold Plus Advanced Band in 2024. Individual honors, our principal, Dr. Piyush Panjara sir, has got the National Building Award from the Rotary Club, Educational Achievements Award from IIC New Delhi, and Jesse Bose Award for Outstanding Performance. HOD of the Year in 2024 awarded to Head of the EC Department. Best Architect of the Year 2001 awarded to Sri Kishore Trivedi for the college campus design. I talk about the research, publication, and industrial impact. V.V.P. Engineering College maintains strong ties with the industry and a focus on innovation. Intellectual property and research, faculty and students have filed more than 14 patents. Staff have published over 40 books, chapters, and more than 1,570 research papers nationally and internationally. V.V.P. staff provides training to engineers at Reliance Industries Jamnagar and SR at the Jamnagar. We have over 120 MOUs signed with industries in the last 3 years. The college has also hosted a robotics lab in collaboration with IIT Bombay. We have an NABL-approved environmental audit cell, material testing lab, and energy audit cell. Our trust is also having an architecture college, that is Indubai Parekh School of Architecture. About the Electronics and Communication Department, it's started in 2001, so we are completing 25 years this year. Department of Electronics and Communication Engineering at V.V.P. Engineering College, Rajkot is one of the most efficient and progressive departments and has been accredited twice by the National Board of Accreditation. The department places strong emphasis on quality teaching delivered by a team of 11 highly qualified faculty members, including 6 PhD holders. Department have more than 30 MOUs with different industries and organizations for conducting skill development programs, workshops, seminars, training programs, and industrial visits. To enhance students' practical skills, 16 different laboratories and infrastructure worth approximately Indian rupees 1 crore 98 lakh have been developed. The department features 3 well-equipped computer centers with licensed software such as MATLAB, LabVIEW, NetSim, Quartus, and various embedded system tools. Students are systematically trained to undertake projects in every semester, ensuring strong hands-on learning and industry readiness. Department has received various grants for minor research program to conduct the Atal FDP. This is the second year we are conducting this Atal FDP. We got grant in the national conference from AICT. We have other seminar grants from CSIR, Rajkot, that is Department of Science and Technology. Department has consistently secured top positions in Gujarat Technological University, results across the Saurashtra region and Gujarat state. Several students have achieved GTU ranks and exposure and received gold medals. The strong academic foundation and technical exposure have resulted in excellent placement records, with students recruited by multinational corporations and core electronics industries. The department takes pride in its alumni network of over 1,700 graduates who are successfully employed in national and multinational companies and have established commendable career records. So this is all about the V.V.P. Engineering College, V.V.P. Trust, and Electronics and Communication Department of V.V.P. Engineering College. Now I am handing over the session to Dr. Charmi Patel, ma'am, and she will give the introduction about and information about the FDP. Over to you, ma'am.
Thank you so much, sir. Thank you, sir. Thanks a lot. Charmi madam, તમારું mic, please unmute your mic, ma'am.
Yeah. I did this. Yeah. Respected trustee Sri Dr. Naveen Bhai Sheth, distinguished experts from the industries, respected principal sir, Dr. Piyush Vanjara, coordinators, faculty members, and dear participants from across the country. Dear, a very good evening to everyone. It gives me immense pleasure to welcome you all to the online Atal FDP program on recent trends in semiconductor technology and the role of AI in chip design and fabrication. Scheduled from 19th of January 2026 to 24th of January 2026. Semiconductor technology is the backbone of today's digital world. From smartphone and automobiles to healthcare system, artificial intelligence, and high performance computing, everything depends on the advanced chip. At the same time, the complexity of chip design and fabrication is increasingly exponential. In this context, artificial intelligence is no longer an option, it has become a necessity in modern semiconductor workflow. The primary objective of this FDP is to enhance the knowledge and skill of the faculty members in this rapid evolving domain. Through this program, we aim to provide in-depth insight into the latest advancement in semiconductor devices, materials, and manufacturing process. We also focus on understanding how AI is transforming chip design workflows from logic design and physical layout to verification, testing, and yield optimization. One key goal of this FTP is to bridge the gap between academia and industry. Often the faculty member, we teach strong theoretical foundations, but the industry operate at its different pace with the real world challenges and constraints. This program is designed to expose participants to actually industry practices, tools, and problem solving approaches used in semiconductor research and development. The technical content in this FTP has been carefully structured to cover both the fundamentals and advanced topics. It begins with the introduction to semiconductor technology and semiconductor industry ecosystem, followed by an overview of the VLSI design flow and the latest trend in chip design. Participants will gain exposure to the basics of AI and machine learning tailored specifically for engineers, and then move on to the advanced topics such as AI in EDA tools, AI assisted design automation, and end-to-end chip design flows from specification to the code and from code to layout using AI. We also cover smart manufacturing and the role of AI in semiconductor fabs, yield optimization, testing, emerging trends in hardware software, co-optimization, and finally, student opportunity and open house discussions, which we believe will be highly beneficial for academic mentors. We are extremely proud to share that this FTP features well-known and highly experienced industry experts from the leading organizations such as eInfochips, Synopsys, Intel, MediaTek, Microsoft, Sangoff, and Qualcomm. These experts have spent many years working in the same domain, handling real-world challenges and delivering cutting-edge solutions. Their sessions will help participants clearly understand what kind of work is actually carried out in the industry, enabling faculty members to pass on this advanced knowledge to students in more practical and industry-aligned manner. Another remarkable highlights of this FTP is the record-breaking participation. We have received overwhelming response with 450 plus participants from 18 different states across the India. This itself reflects the relevance and importance and timely nature of the chosen theme. Dear participants, your enthusiasm and eagerness to learn truly motivate us. We sincerely hope that you actively participate in all the sessions, interact with the experts, and make the most of this learning opportunity. With this, I once again warmly welcome all the dignitaries, experts, and participants. I'm confident that this FTP will be a valuable, enriching, and memorable experience for everyone involved. Thank you, and I wish you all a very successful FDP. Thank you once again.
Thank you. Thank you, ma'am.
Thank you so much, ma'am. And I would now like to request our Honorable Trustee, Dr. Naveen Sheth, to enlighten us and bless us with his words and wisdom.
Namaskar. Very good evening. My audio is clear?
Yes, sir.
Yes,
My
sir. You are audible.
Okay. Okay. So it's my pleasure to be here in this FDP organized by the V.V.P College. And I also welcome all participants across the nation. Respected Principal Sir, Coordinator Sir, Head of Department, all participants, eminent experts, and all faculty members. So today, I also congratulate the AICTE. AICTE is providing the facility to the different colleges, and by this way, the technical teachers, engineering college teachers, polytechnic teachers, they are upgraded by this type of the FDP. In NEP 2020, the teachers training is also very, very important, and the focus there in NEP 2020. For that, the various institutions are working for that, but the AICT is working hard to upgrade the skill of the faculties, to upgrade technically the technical college teachers. So in that line, this FDP is supported by the Atal FDP by the AICTE. The semiconductor, the topics selected by the V.V.P Engineering College and the organizer is very important, because this semiconductor previously means even today it is 100% important. So now India is working hard for the import substitutes. In case of the defense, we are largely success, and number of items now we are manufacturing here in India. Same way, we are the largest manufacturer of the mobile and number of other devices also. Similarly, in coming years, the semiconductor is also one of the important device to be manufactured largely in within the country. There is a government provision there in the Uttar Pradesh government. There is a semiconductor park is inaugurated. Same thing, the government of Gujarat, they have also provided the facilities for the semiconductor manufacturing there with Dholera and other areas. So it's a important things. So to get the knowledge of semiconductor devices to manufacturing and other thing. So this type of the FDP will definitely help. The objective is already given by the Charmi madam, that it is provide the platform to the from the different discipline. Means it is even the important thing that the person from the computer science, person from the material science, the faculty from the electronics and communication. So all these are, means it is a multidisciplinary events, particularly as which is one of the reforms in the NEP 2020. So definitely the lecture delivered, they are also from the prestigious institutes and the large industry. So definitely this FDP will be most useful to the faculty members, and indirectly it will be helpful to the students, and by and large it will be useful to our nation. Thank you very much for providing me this platform to interact with you. Thank you. Bharat Mata ki Jai.
Thank you,
Thank you.
sir. We are indebted to your motivation, sir. Thank you so much. Now this is Dr. Sneha Pandya. I would be extending my vote of thanks to one and all, and quickly we'll start our keynote session. So first of all, I would like our trustee, respected Dr. Navin Sheth, sir. I'm thanking you on behalf of the department and all the faculties, because you have always been, you and all the trustees have always been the motivating factor, and you encourage us to do the wonders that we may achieve. I would like to extend my thank you to our Honorable Principal, Dr. Piyush Manzara, sir, for always be guiding us and enlightening us, and never allowing us to stuck anywhere, always guiding and helping. Our department's pioneer, the Professor HOD, Dr. Paresh Dholakia, sir, for today's enlightening words, as well as all the support that we have been always needing. EC department staff and all the college staff for always be there with us, and none other than like we are a team, but we are thanking and extending our thanks to all the participants here, because it is you due to whom we have been encouraged to give you the best, and we are actually putting all our efforts. So the 468 and counting are all there, to whom I am extending my thank you on behalf of the coordinator, Dr. Charmi Patel, and myself, Dr. Sneha Pandya. Last but not the least, it is always about Atal and the AICTE platform who are enabling us to do such insightful sessions, making the world a small place. People from Tamil Nadu, a speaker from Gurgaon, someone from Mizoram, and connecting them from Gujarat. It's a wonderful feeling. And I am sure you all are going to be the part of this and you will be gaining a lot being the part of our FDP. Our speakers, our respected speakers, thank you is just not enough for them. So I'm not including them here because our gratitude is far beyond the words. And I would just share that so many of them are our valued alumni as well. So now, in no time, we are going to start with our session. Our keynote session is to be taken by Mr. Nilesh Ranpara, who is the Technical Director from E-Infochip Semiconductor Department.
Our keynote speaker is just joining within a minute. Please wait for a minute.
No, ma'am, you are not audible.
No, madam, not audible.
Is it audible now?
Yes, madam.
Thank you. Very soon, Mr. Nilesh will join us. And at the end of the session, I'll share the link of the feedback form in the WhatsApp group. You all are supposed to fill up the WhatsApp, taking that from your WhatsApp. And at the end of the session, we will all turn on our camera for a short while for the purpose of the attendance.
Hello.
Good evening, Mr. Nilesh.
Hello, good evening. Good evening, all.
We are all privileged and blessed to have you as our keynote speaker. To everyone, I would like to introduce to you our mighty speaker, Mr. Nilesh Ranpura, who is a Senior Director Engineering in the company of E-Infochip, which is an aero adventure. He is in the Department of Semiconductor. He has more than 25 years of industry experience, and he is actually driving, leading, and executing the semiconductor products in the area of data center, high-end networking, IoT, mobility, consumer, healthcare, and automotive domains. Architecturing VE, design IP, design for taste and physical design for projects, and extensive working experience in Silicon Valley, USA, Europe, Israel, and Japan are the attributes of him. He has strong execution towards the performance evaluation, cross-functional teams, turnkey execution in the era of RTL, GSII, EXIC, and can I please request? I would request network administrators sir, to mute the participants if they are not muting themselves. Kindly ensure your mic is muted. You are disturbing everyone, please. So sorry for this interruption. So basically, I was introducing Mr. Nilesh Ranpura. He has the strong execution towards the performance evaluation, cross-functional teams, turnkey execution, that is RTL to GDSII, ESIC, and semiconductor parts, and driving goals of the organization. He has written more than 10 plus international papers. He did his graduation from DDU, Masters from SVNIT, and his MBA from IIM Ahmedabad. Truly blessed to have you with us, sir. Over to you.
Thank you. Good evening, all. I really appreciate the way FTP is being conducted, matching everyone's time. So I will be representing several insights from industry, which will be purely from industry, and you can ask questions. I may not be able to see the raise hands, but if you can speak while asking, it will be much more better. So with that, I'll start my presentation.
No worries. We'll, if there are questions and if you are not able to see them, we'll let you know them.
Yeah, if somebody can, convert into a voice and or ask straight away, that is fine. Okay.
Sure.
So my topic today is technology inside GDP and opportunities in India and everywhere. So what is happening around us? If you see around us, we see many products, and that's what's happening for last 20 years. You see this kind of advanced products like RoboCart, which works like a cart and it has robotics approach. You will see sophisticated helmets available in Korea, Japan, Taiwan, which has Wi-Fi, front camera, back camera. So it makes the highways and driving very safe. Unfortunately, it is not available in India, but those countries have this kind of technology and makes the safety first. And you can see the accidents happening on the roads in India. So these are a few products which has been developed by us in the last 9 years. EV has everybody's talking about EV car. It is already on the road by Tata and other people. Now even racing car is available in EV category. That means the batteries can catch up the speed very fast. Nissan and other companies are already doing the racing EV cars. Trucks are no longer left behind in the EV category. So the trucks available from Tesla and other companies are going into EV. This means EV doesn't mean only two-wheeler or four-wheeler. EVs goes in the whole transportation industry. Again, these are products, products, and products. That has also extended another kind of transportation called aircraft. This is an EV aircraft which can fly for easily 3 hours on a one charge, and it has been experimented and it's working out very well. Space tourism has got a momentum since last 7 years. The global market for space tourism has gone to more than $250 billion. And all the space tourism are being controlled by the products what we develop. Single ticket for space tourism is $30 million. That amounts to around 27 to 30 crore per seat. But people are crazy. There is a queue and everybody's in the queue. But this is one kind of transportation. What I'm trying to say is these are all transportation devices which are converted into EV. What kind of device you will call this? Again, same, human transportation. This has been demonstrated at many places. The sophisticated control system available on the body is part of the high technology design. Again, it's a transportation. If you look at any car these days, this is the antenna consumption in the car. Any high-end car will have this kind of antenna. For example, fan beam antenna, patch antennas, adaptive antennas, smart antenna across the car. More than 8 antennas are very common in the car. You may see them as a fin or a plastic fin, but they are actually 6-fin one combination antenna. So this is how the products are being seen around us. This is another example, SpaceX cockpit. You can see from this SpaceX cockpit is completely technological view. It has specially designed Apple's iPad, the small size and the large size, and the pilot can operate just like playing a video game. Of course, with a lot of discipline. And more than that, going towards a product where astronauts do not even fly. The robots becomes astronauts and they go inside the space shuttle. These are all products existing, working, and we have been developed directly and indirectly for our customers. Again, the theme is same. What do you see around us is all products, products, and products. One more, AI. Everybody's talking about AI. And what is the engine behind AI? Of course, the engine behind AI is multiple chipset from multiple manufacturers. Like NVIDIA is leading the chipsets, AMD is leading the chipset, Intel is leading the chipset. You can see the programs 2021 to 2023, how much of billions of dollars they're putting up into the AI chips. When there is a lot of focus investment, and that's how the AI is coming out very well in all the areas of humanities. So what is common in all these things? Very easy. These are all technology-based products. They are designed through a technology. These are systems, systems comprising of electronics, software, and sensors. So, okay. So,
Yes, sir, you wish to say something?
no, I think somebody muted my microphone, so I just unmuted them. Were you able to
Okay.
listen my words? Yeah.
Yeah. You're very
Okay.
much clearly audible. Yeah.
Okay. So, and in this hardware and software combination, the common is chips, which is the heart of the product. Typically, semiconductor chips are into multiple category. It can be wireless interfaces, microcontrollers, and it goes into all the application, which are existing platforms. Typically, platform one is all kind of CPUs, which is MPUs, MCUs, DSPs, DPUs, multi-core systems, and chiplets. Then comes second platform for semiconductors interfaces like PCI Express, UCI, CXL, Gigabit Ethernet, and multiple buses like AHB, PCI, various kind of sensors. In fact, these are few examples. There are more than these 7 sensors. Application of the chips are endless. It started with the wireless communication, space grade chips, LED driver and radar chips for automotive, Industry 4.0 chips, high-end processing SoCs for AI, ML, and GPUs, especially fully autonomous chipsets for EV, underwater functional chips, healthcare, wearable chips, and it's growing application-wise. What are the insights from us as industry in coming decade? There are undercurrent usage models in various areas. Key driving forces are rising consumption of electronics in all the area, including defense, increasing number of demand in all the economies, Asia, Africa, Europe, everywhere it's increasing demand of electronics, or I would call it technology. They're expanding newer and newer applications like drone applications, space applications, robotics, unmanned aerial vehicles, and many new. Fourth, new geo-economical reordering is also causing increased diversification on electronics. The most beautiful part is 75% of this is happening Asia Pacific, where we are located. Take an example. Defense. Many of us see current conflict as war. There's also another way of looking at it is called defense economy. Military spending of 2022 post-Ukraine war see United States the highest budget, followed by China, Russia, and other countries. And see who is consuming highest, Ukraine. This means everybody is supplying the weapons to Ukraine and other countries and making this economy very live. Again, I'm saying you may see things as a conflicts or a war, but in economy, this is called defense economy. See, global military spending is more than 2 trillion. First time in the history, $2 trillion. And you can see the statistic, US, China, India, Russia. Every country is now upgrading their weapons because they fear that the old cannonballs, bullets will not work out. Everybody will need drones or many other things. This is one of the very growing market called defense economy for technology. AI is the second largest market, growing at a very high speed. It is going to reach $250+ billion by 2032 and maybe more. Post AI area, there is another impact called aviation industry. This is also called economy. There are 39,000 planes going to be ordered in next few years, which will generate $5.9 trillion economy. Look at this, $5.9 trillion economy. Every aircraft is 10, 20-year old. In the next few years, which country is going to order how much is shown here. Asia is highest, 15,000, followed by US and Europe. This is a big economy. Again, in every aircraft, 30 to 40% components are all technology. Rest all is mechanical and engine. And these are all proven data. You can refer to Boeing's website, Gartner, or many other data analysis websites. Drones are not left behind. The drone economy is again growing at a very, very steady pace, and it is having $13 billion market, and it will continue to grow and grow with the defense economy. Space, again, as I said, $344 billion market in the space, and it's growing incrementally. Let us spend some time on this graph. As an industry, we have observed from last 25 years, January 01, 2001 till now. There was a first recession, many of you might have seen, called dot-com recession, which happened in 2000, 2001. The second recession happened in 2009, great financial recession by Goldman Sachs and other companies. Then we had a smaller recession in COVID time, and now then we are growing here. In all the three recessions, you can see the worldwide semiconductor sales is moving upward. Worldwide unit sales is moving upward. This is a sign that semiconductor or technology industry is actually recession proof. When the recession come and go, it has always grown in the last 2.5 decades. Whether academia shuts down the electronics branch or not, this recession is never impacted the economy. This is a very important slide for you all to understand, because economy is at the end driving everything. And you can see semiconductor or technology industry is left untouched. How GDP is structured nowadays. GDP is a foundation of economy, and technology is #1 impactful sector. As I explained, markets are growing in multi-billion fold in India and outside India. In India, our respected Prime Minister Narendra Modi ji has set up manufacturing vision with India Semiconductor Mission in 2022, creating ecosystem, and we have now started investment happening across the country in many areas like fab and OSAT. So if you see this larger green circle is the mainstream economy of India, which is primarily agriculture and other components. Inside there is a MSME. Inside there is design, IT, and manufacturing. And the central core theme is going to become semiconductor-based economy. Because this is the area where multi-billion dollars are kept in India as well as world, both. There's another way to look the same, GDP, economy, and technology. Look at the world scenario. The top 25 companies in the world, if you see, all tech companies. They all have semiconductor. They all have software. They all have systems. They're all having advanced technology, AI, or chiplets, or many. These are the top 25 companies. Then, of course, comes Aramco, the oil company, and other companies. Even if you see 50 largest companies in the world, you see the same scenario. The technology is dominating the economy. This is the example. So the technology is going to be a foundation of economy, which will drive GDP. This is the view of how chip industry is growing in the world. By 2030, it is going to become $1 trillion, growing at the 8.6% rate. And it has following area like home appliances, industrial, automotive, server and network, computing devices. Each of this segment will grow in the semiconductor industry. So this is an extremely bright future for semiconductor. And this is told by PricewaterhouseCoopers based on all the statistics they get from manufacturing and design companies. How this technology ecosystem is constructed. We call it ESDM, Electronic Semiconductor Design and Manufacturing. So primarily it has markets. The markets are basically healthcare or gaming or defense, etc. These markets are supplied by 4 foundations. IDM, Independent Design Manufacturers. which has companies like Qualcomm, AMD, foundries like TSMC, USMC, UMC, SCL, Chandigarh, etc. And to these IDM houses, there are more suppliers like gas suppliers, chemical suppliers, wafer manufacturers, instrument suppliers, packaging chemicals and metal suppliers, and many ancillary industries. Then there's a larger ODM houses, outsourced design and manufacturing companies, where ancillary components are made, PCBs are made, complete products are made like Foxconn, Celestica, TDK, Jabil, etc. And in India, we have Imtron, Windrox, etc. This is the second foundation driving this market. Then the capacity creation is where academia and skilling institutes come into the picture. And fourth is supply chain, where infrastructure plays a key role like airport, road connectivity, and multiple other foundation. These four foundation will grow when this market will grow. And hence it is impacting the whole economy. This is how the ESDM ecosystem of this market is driving supply chain, capacity creation, ODM and IDM. And this is going to remain for next 20, 30 years because this existed even before 20 years in other countries like Taiwan and USA. Now it is entering India. The most important factor, advantage India. We being a country has our own robust demand, strong demand of electronics, technology, software and systems. We being in India, we have competitive advantage. We have kept millions of dollars of investment. We have strong academia. We have been delivering to the GCC for many years, including in India, outside India both. The present government has high motivation to grow through a policy support, and there's an amazing policy support available for India. And more, post-COVID, there are lots of investment happen from FII and many other places. So this way, India has an advantage India concept, and that's why we are in the center of this growth. Example is here. This is the first made in India chips developed by various institutes. And this was demonstrated in Semicon India, New Delhi by Shri Ashwini Vaishnav and our Prime Minister. So this is not just talk or on paper. This actually has executed and delivered. All of us know, but I'll still capture here that India is growing on the ground level for India semiconductor mission. In fact, in every region of the India, there is something or other thing coming up. With Gujarat having fab in Dholera, OSAT in Sanand, following by Maharashtra having different plants, Karnataka having plants and GCCs, Tamil Nadu, Andhra Pradesh, Telangana, and Uttar Pradesh and Assam. These are all being announced and DLI, PLI skills are applied. And our India's semiconductor revolution started. These big companies are few names. There are other companies as well. Is shown here. These are small startup companies in manufacturing area. Till today, we have companies like CG Power has invested 7,600 crore. Keynes has invested 3,400 crore. And there are multiple other companies who have invested in India. And they are going to grow this investment as the market grows. Talent snapshots. These are various insights given by India and abroad both. For example, here, this is a chip industry gap in US. They have at present 67,000 jobs, which is unfilled, and then it's growing and it will have more jobs available but not fulfilled. Same thing in Europe, same thing in Asia, Europe and Asia. We have 10 lakh jobs in North America getting created by 2030. And everybody knows that USA doesn't have so many workers, so they will rely on Asian workers. 1.5 lakh jobs created in Europe. 5 lakh jobs creation in 2030 in India. And overall Asia will have 10 lakh jobs created by 2030. This is the strongest talent impact. These are minimum number we are suggesting. the number can go above as well. So fabless companies and fab, they are a golden expressway for all of us. So if you have students and they are idle or they are not feeling good, tell them don't just worry and sit inside. In fact, tell them that go out, meet people, explore, network, attend seminars and conference. And tell them that you as a student, you as a faculty, you as an academia are in the center of this growth. Everyone has to see long term, not the 1 year, 2 year. If you see decade, you are into the center of the growth theme. And who will do this? Multinational companies, India semiconductor startups, research organizations like ISRO, DRDO, India semiconductor manufacturing houses like fabs and OSATs, and many other ancillary industries. They will do the hiring and talent acquisition as well as partnership. With this, I'll say future is fantastic. Who will drive this future? The answer is very clear. The future will be driven by systems. Systems comprising of software and semiconductor. And this is one sample example we have given, that at present 10 million mobile phones, 10 million EV vehicles, 15 million consumer products are being needed every year. This means there are 120 billion systems needed. And you count few chips and few sensors inside this 120 billion, then we need 600 plus million sensors and silicon and lots of software to drive them. That means this is a future. And I will not talk about quantum today, but quantum is additional layer of growth for all of us for silicon, software, and system. This means if there are more challenges, there are more opportunity in our platform. Silicon, software, and system is a very unique combination of building nation's economy in coming decade, apart from traditional way like agriculture. So with this, I'll pause it and I'll keep it for discussion on any technology, business, or any area, or any questions if you have.
Is anyone having any query?
Yeah, Vijit, go ahead.
Sir. Sir.
Yes.
Nilesh,
Sir, we also have one area of understanding that in defense, missile technology is also playing a very crucial role currently, current scenario. So we have also opportunity there for our students.
Yes. See, as I broadly said, the whole defense area, starting from the attacking devices like AK-47, missiles, tanks, all kind of vehicles, all kind of instruments, they have enormous opportunity. In fact, there are already electronic guns have been made by India. So for missile launching, answer is yes. But compared to missile launching, the new area is emerging is more on drone side because it is working very perfect for a very near distances. Missiles are primarily for the long distance fight, but that happens when larger conflicts are happening. And the consumption of missiles are always like 1,000, 5,000, etc. But the other ones like drone and other, they are 1 lakh, 2 lakh, 5 lakh, etc. So the scope is there. Yes, answer is yes for missile, but the larger scope is on the drone side.
Thank you, sir. Thank you, sir.
Nilesh,
Yes,
sir.
Dr. Kirit. Yeah.
Nilesh, sir. As per your analysis, and I came to know that there are a huge manpower requirement by 2030. And obviously, being a responsible academician and institution, we have to take care, we have to train our students accordingly. then and
Yes.
then we can power up our economy to have a better push.
Yes.
But to be honest with you, it looking to across the country, that scenario of the academies are not that suitable, and the syllabus is, there is a huge gap between the syllabus, traditional syllabus what we are teaching, and if we are looking at industry ready manpower. Can you suggest some, because see,
Yes, I understood.
it doesn't work that having a seminar and all this thing, this will not
Yes,
create
yes.
that skill what actually the industry is looking for.
So, Dr. Kirit, I really appreciate very candid input
Mhm.
and accepting that gap. It is very important to accept the gap. That's a first step of
No, I'm
progress.
really worried about it because
Yeah.
there is a huge employment opportunities, and we don't have the skilled manpower.
Correct. Yeah. So there are two ways. One of the best ways, lesson learn, and second way is a top-down approach. So lesson learn means the developed countries have very closer industry academia partnership. That's how they have grown. So that's what we have to start doing as a lesson learn, both beside academia and industry. And some of the academia is doing, some of the industry is also doing, but the intensity has to be more. That's one input. The
Exactly.
second one is the top-down approach where Government of India, ISM, they have started putting UGC and AICT courses like electronic VLSI design, special UG courses for VLSI design, MTech courses for VLSI design. So those are just started. Of course, just started.
Exactly.
It will take some time.
Because in framing syllabus and all that, industry should also come forward and give their input so that we can have the industry ready manpower.
Yes, in fact, we'll be going one more step, not just only curriculum, but we'll be working hand in hand to drive certain subjects till the time the faculty pool is ready within the academia fraternity. So basically, idea is to work like a equal footing partners, not as a walled forts. Is the time of today, and person like you will be the more pivotal, I would say, person to do such
Thank you,
activity.
sir.
Yeah.
Thank you.
Yeah. Thank you.
Anyone else? Do we have anyone else with the queries?
No problem.
Okay.
And in case if you have any time later also, please
Yeah.
send it to Sneha, and I'll be
Sure,
happy
sure.
to answer.
Yeah.
All of your wonderful audience, thank you for your great resonance at 7 p.m. and attending this is a fantastic enthusiasm. Thank you, Dr.
And on
Sneha,
behalf of
Dr.
all of
Charmi,
the
and Dr. Paresh.
yes. On behalf of all of us, thank you for taking out your time. I know how busy your schedules are, and we are indeed indebted to your session. Thank you so much, Nilesh.
Thank you. Thank you.
Thank you, sir.
Now we have a time to turn on our cameras, please, so we may see each other. Just for a while, we'll all turn on our cameras before we already have our second speaker on board, but before I can introduce him to you, we'll have a quick photo session. Am I audible to everyone?
Absolutely, yes.
Yes, yes, sir.
Yeah. And there are few people who are also trying their best to look the best before they actually can turn on their cameras. Yeah.
Academics are always best.
You, sir. Okay. Thank you, everyone. I'll be just putting the link of the feedback here in the Teams now. And in 5 minutes, we'll begin our next session. I'll be just putting the link of the feedback soon.
Ma'am, the chat box is not.
Chat box
It's
is
a,
not enabled.
yes,
Just a
ma'am.
minute. Give me a moment. Give me a moment. I'll do something.
Yes, Kirit sir.
Yeah. Yes, ma'am. Do you want to say something?
No, you have raised your hand, so I thought.
It was earlier. It was earlier.
Okay,
It,
okay. Yeah.
huh.
We are trying to enable the chat, just 1 or 2 minutes. Otherwise, we'll send the feedback link through any other medium. Please be with us. 2 more minutes. We're inspecting what's going on with the link. Yeah. While our network administrator, sir, is working with the link, let us just move ahead with our session 2. And let me introduce you to our speaker for the next session, Mr. Karan Shah. Karan, are you there?
Yes, ma'am. Am I audible?
Yes, you are. Yes, you are audible.
Thank you.
So let me first give you the introduction of Karan. Karan Shah has completed his bachelor's in electronics and communication from the V.V.P. Engineering College, Rajkot, Gujarat, and the University, Gujarat Technological University. He has started his career in semiconductor industry with e-info chips before 14 years. So he's having 14 years of experience in physical design as well as EDA domain. Over the course of years, he has successfully contributed at Juniper, Qualcomm, Intel, and Synopsys. So he is an ex-Synopsys employee now with his technical expertise in SoC design, planning, and 3D IC designs across the tech nodes ranging from 130 nanometers to 2 nanometers. In his last organization, Synopsys, he has partnered with multiple customers like startups, government organizations, hyperscalers, and foundries to make them successful in their product designs from RTL to GDS2. In today's session, he will be guiding us and covering the semiconductor technology landscape with its bright future and the rich history, emphasizing its key role in the academia. His 14 years of experience is surely going to enlighten us today because he is someone who has started from the scratch and who is going to guide us about his journey along with this important topic. Karan, can you carry forward from here?
Yes. Thank you so much, madam, for the very nice introduction. And I'm very proud of being an alumni of V.V.P. Engineering College, and really, really thankful for inviting me to such a prestigious forum. So thank you so much to everyone, and very good evening to all of you. So today I'll be discussing about the semiconductor ecosystem. You already got a brief of a couple of things from Mr. Nilesh Ranpura, but I will be diving a little bit into the technicals. And maybe for next a couple of days, that is next 5 days, you will be looking at the similar set of terms, jargons, crosslinks, etc., 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 for the reference purposes. So I will, so in terms of any questions, please raise your hand or unmute yourself in between and feel free to ask so that I can answer the questions immediately. On top of that, I'll be just switching off my video for now because to have a better latency to project the materials. And later, once we have an open forum, then we can enable the video once again. So let me know once you are able to see my screen. Is it visible?
It is visible.
Yes, Karan, sir.
Okay. So semiconductor technology and the foundation of the modern electronics. So the overview of the presentation will be divided into 6 sections. First, we will go through the industry overview. How does the industry look like? Market trends, and what is growth projection and 2030 and beyond. Because if you do not know the future, then you will not be able to understand uh, what is the valuation or where as a academia you need to focus on. Once we cover the industry overview, we will dive into the historical evolution of the semiconductors, key milestones, what are the achievements that have been done by the historians as well as scientists, and where we are as of today. Then from there, we'll move to the material science. What are the fundamental building blocks of the semiconductors and how this complete gamut of things works. Afterwards, once the material science is completed, we will dive into the manufacturing process. Once the manufacturing process is very elaborate, and you must have heard that it's very expensive term. So we will discuss about what is manufacturing, lithography, yield management, clean room environments, etc. Once that is done, we'll move to the advanced packaging. And once the advanced packaging is done, we'll move to the future trends. So out of everything, each and every topic has so many subsections. And in this so many subsections, there are so many opportunities as an individual, or I would say as an engineer, or as any of the individuals. So I will be discussing as well what are the opportunities a job seeker should search for. If somebody is in MBA, there is a definitive opportunity into the domain of the semiconductor. So ranging from the blue collar workforce to the highly skilled scientists, this particular industry covers each and every opportunity possible on the land. So moving forward, I would like to discuss the scale of time. So without any reference, it is very, very difficult to understand what we are dealing with. If I show you the scale of time, then with context of the time, you can visualize how the industry is moving. So yes, everybody is familiar with time. Everybody knows how to see the time. And we know that our universe was formed 13.7 billion years ago. And out of 13.7 billion years, our solar system was formed 4.6 billion years. So this is the time scale that we know that, okay, there is a 4.6 billion years ago, we have the universe, or I would say solar system, which was formed. Now, with out of 4.6 billion years, the human history is just 2.6 million years. So you can see that it is 13.7 billions to 2.6 million years. So this 2.7 million is just a tip of the 4.6 billion years, or I would say even a very farther tip of 13.7 billion years. Out of 2.6 million years, we know what is the recorded history of humankind. The rest everything is prediction. Dinosaurs, yes, those are prediction itself. So the recorded history is just, I would say, a 6,000 years. So from the 4000 BCE, we have nothing till 2000 BC, and out of 2000 BCE, we have everything recorded. And out of everything, right, the average span of human life is 100 years. So if I compare our average span of human life, that is 100 years versus 13.7 million years, the human life is very, very small, even a fraction of your thickness of hair, your hair on your head. That's the human life in comparison of time compared to the universe. And we have a lot to achieve in this 100 years, and we have a lot to do. So you can imagine the scale of 13.7 billion years to the 100 years. Now, coming to this analogy, I am going to explain the scale of the transistor. So the wafer size which we take on where the transistor is being drawn, the wafer itself is 30 centimeter. That's one particular scale, I would say, the scale which we use to draw a straight line. So 30 centimeter is the diameter of the wafer. Our human blood cells are 700 nanometer, so that is 7 mm. The transistor is 3 nanometer. That is what we are manufacturing as of today or as we speak. So that's the scale of transistor. It's a very, very small dimension. It is very difficult to manufacture. And even once manufactured, it is very difficult to ensure that it is functioning correctly. Now, once it is manufactured, it does not guarantee that whatever is manufactured, first of all, you can't see it. If you can't see it, how do you test it? If you can't test it, how will you verify whether it is working, how much time? And if you don't know how much time it is working, you cannot predict the lifespan of the product. So, yeah, everybody has figured out this complex process, but to compare a simple thing compared to the wafer, which is 300 mm, our transistor is just 3 nanometer. And that's what we are doing as of today. Now, coming to the trends, I hope just the analogy is very much clear to every one of you. Now, coming to the industry 2030 and beyond. Now, future is important because if I do not tell you the future, you will not know what to teach in the academia or what is coming to I would say India or what is coming to the ecosystem. And if you don't know that what is the bigger scale, then it is difficult to tell the next generation that hey, this is coming and this is where you should invest or this is what you should learn. So as of today, the valuation is around $700 million, sorry, $700 billion of the complete industry, and it is expected to hit $1 trillion. So the growth in next just 4 years is almost, you can say, double. So we were 2024 at end of the 2024, we were around 600, and we are almost shooting to 1.2 trillion by 2030. So I would say it's an exceptional growth that the industry has foreseen in last 10 years. From 2020 to 2030 is one of the record-breaking year, or I would say record-breaking decade of the semiconductor industry. Now, where does the semiconductor industry is investing itself? So first of all, the out of complete revenue, they are investing almost 50% of the revenue in R&D spending. So this is huge. When R&D is there, that means academia as well as the rest of the complete ecosystem has to invest in the R&D and bring up the future, or I would say bring up the innovations that will turn your future lives in ease. So what are the challenges which we are facing as of today to scale this? The one which you have heard during the COVID times as well as recently, that supply chain is a constraint and everybody is fighting about, I want this piece of land, I want this piece of land, or I'd like to have this country. And we have so many tensions growing in the areas of the Taiwan and rest of the geographies. I'm not sure if you're aware about the Ukraine. Ukraine is one of the prominent supplier of one of the key component of semiconductor manufacturing process. So geopolitical tensions are very high across the world, and that has led to the chip sovereignty campaigns. So all the countries are doing that, okay, I want chip on my land, I want to invest here so that tomorrow my rest of the supply chain is not stuck. So regional manufacturing capabilities are expanding. That's what is happening in Dolera. In Dholera, we have a plant which is upcoming. So that's the main important factor for the security of the supply chain. As the facts, 90% of the APEC companies are saying that the talent is a top priority for the sustainability, and 63 companies saying that there is a risk of retention for the highly talented engineers. Even Mr. Nilesh Ranpura has rightly suggested that there is a talent shortage and we need to work towards it. And this has become the topmost C-suite discussion, saying that at the CEO level, the discussion is all about, I have a talent crisis, how do I solve it? So training is a challenge, hiring is also a challenge, and retention is also a challenge. Because in this section, or I would say in this particular industry, the data is very, very confidential. So as a as an engineer of any of the reputed company, I cannot share what work I'm doing as such. I can just give you just the highlights. But if let's say there is a student who has completed electronics and communication engineering, or who has completed even masters in semiconductor or VLSI technology, will not be ready on the next day when he or she comes to the industry. It takes minimum 1 year of a time frame to train a fresher, just to ensure that he is up to the speed of what the industry demands, even though he is highly trained from the highly reputed institute of the world as well. Because this industry progresses so fast, and the security around everything that is being done is very, very tight. So the knowledge transfer that has to happen is very, very limited. And somehow we need to come together and solve this problem. Coming to the history of the semiconductor, I think I have just given the overview, first of all, the nick of time, and then, where future we're trending. But then we need to start from the basics of the transistors and where it started. So 1940 at the Bell Labs, the PN junction diode was invented, and it was really an accident. So they just demonstrated that they had a cut in the silicon, and there was a light which was getting emitted through that cut. And that movement was identified as an PN junction. So it was an accidental discovery of the PN junction diode. And this PN junction diode has revolutionized everything. After 1940, we have 1958 and 59, then where we had a first chip. And that first chip was demonstrated the foundation of the semiconductor industry. And after that, 1965, the Moore's law, that the transistor will be doubled at roughly 2 years, and specifically 1.5 years is what they have imagined. But there's the major part of the uh, basics of the semiconductor. That's where it all started. And after 1965, there is no looking back at the innovation as such. Now, this is what we started, and now we need to see what continued after that. In 1971, our first commercial microprocessor by Intel, 4004, having just 2023 transistors on top of that. That's just a handful of transistors. Today we have trillions of transistors, not even billions. We have trillions of transistors on one single chip. So every decade there was a disruption, every decade there was an innovation, and every decade there was something new to the world. In 1980s, we have seen the first PCs by IBM and Apple. That was, so you can think of, from 70 to 80, just in 10-year time frame, there was a very tiny microprocessor, and from the very tiny microprocessor, there gave a birth of the complete computer, or I would say PCs. In 1990s, because the PCs came, there are other components which started, in terms of the demand, and the expansion of the fabless companies started from 1990. So previously there were very handful of companies which had their own private fabs, private design centers. After that, a pure play fabless company started. So when I say fabless company started, that means there was a dedicated fab also started. Okay. If there is a fabless company, then there would be an counterpart who manufactures the chips. And that counterpart was, if you can guess, it was a TSMC. After the TSMC has gained momentum in 2000, we had a foundry war. So everybody was trying to chase this transistors, small and small transistors, and also came a mobile revolution. So mobile was a very, very, very good device, which has again uh, gave a complete new angle to the world, and everything was coming to your hand. Previously, there were no smartphones, there were normal phones, and then it came the smartphones. So that revolution has changed everything. So previously, your PCs were used to be plugged into the electronic, or I would say electrical system. The mobile was a charge and go system, which was, it was kind of a mobile device. A mobile is ideally a word which is something which is continuously moving. So that mobile revolution has once again changed the world of the semiconductors, where it has started focusing dedicatedly on kind of a low power devices, and that's where again the low power started. In 2010, we had a CPU as after the era of mobile, right? If you remember that now you see the mobile phone is around, 4 gigahertz, Qualcomm processor. It has so many CPUs, so many GPUs, and also the AI module, whatnot. But the CPU war started back then, and at that time itself, the RISC-V processors were also started in the late 2010s, and that was the main again the function of competitors of your x86 architecture. That was the ARM architecture which got famous because of the handheld device, and it's a low power capabilities. So even as of today, the low power capabilities are held by ARM as well as the RISC processor, and 2020 and beyond. So this era, right, it's a quantum leap. We are calling this a quantum leap. And from 2020, we have seen all kind of processing unit wars. So some companies, in the AI, definitely AI, you need the GPUs. Some of the companies are making their own DPUs, data processing units. You must have heard of Google making their own TPU, tensor processing unit. So all kind of different processing unit to ensure that their processor, or I would say their chips, are smarter or way ahead of the rest of the companies, or I would say it is an application specific demonstration of the processing power. And then is coming is 3D IC. So we will talk about 3D IC as well later in the session. And finally, the quantum leap. So qubits are the future as well. I think we'll discuss in detail in upcoming slides. Now to the fundamentals, the materials. So until unless we learn silicon and other materials, we are not going anywhere. So silicon, the oldest material, and my question would be, why silicon? Now, the reason for the silicon is, first of all, the bandwidth is very reliable for the manufacturing of the chips. The second one is abundance. Anything and everything which is there in huge quantity is always easy to grab. And if something is in huge quantity, then definitely the cost would be very, very less. So for any kind of commercial sectors or any kind of commercial part, the cost would be the driving factor of many, many decisions. So that's the fundamental building block for the silicon. Other than that, there is one more important factor which the rest of the material does not have, or rest of the compounds does not have, I would say, is when silicon is merged with the oxide, it forms a very good insulator. So the SiO2 is one of the powerful factor, or I would say a powerful material for the making of the chip. And that stability gives an upper edge and the revolution that we have so far achieved as of today. Now, coming to the next set of things, right? Just silicon is not enough as of today, because we have moved from normal silicons to different wants. We want solar power, we want EVs, we want different power grids, we need fast charging devices. So this all combination has led to various different materials that has different electrical properties and can handle different temperatures or different voltages. So silicon carbide is one of the emerging, or I would say, it's a very stable product, has a very good band gap. Because of this band gap, you can see it can tolerate very high voltage and temperature, and it has a lesser power losses. So silicon carbide is extensively used in electric vehicles as well as solar inverters, power grids, wherever you need to switch between the power grids. So let's say uh, you want to switch between one voltage supply to different voltage supply. That's where the stability is needed, and silicon carbide is used in abundance. Gallium nitride, again, very a high tolerance to the voltage and temperature, are used for the fast charging purposes, RF amplifiers, and 5G base stations. It's being heavily used, and these are all small power units or efficient power electronics. The gallium nitride is used. Gallium arsenide. So if the smartphone itself has so many chips inside it, and one of the major module is RF communication. And RF communication combines on top of your chip. So there is a digital module on top of that, which there is an analog module which sits. So when you need to communicate with the multiple frequencies, that's where the gallium arsenide is used. And majority part is the communication when you want to transfer from digital to analog. That's where the gallium arsenide comes into the picture. Germanium. So now you must have seen that the EVs are also taking decisions at the night, and those night visions, you need a very sensitive substances which can detect your light and change the state, that is changing 0 to 1. So these are infrared sensors, night vision cameras, and fiber optics. That's where the germanium is heavily used. And as soon as it detects the light, you can see the band gap is very less, so it's easy to switch from 0 to 1 or 1 to 0. Indium phosphide, again, it is used for long haul fiber optics. Now, long haul fiber optics, you might see that within the city. No, I would say under the sea, wherever the fiber optics are used, that's where highly efficient materials are used, and this carry I would say terabytes of speed for the data transfer. And finally, silicon germanium. This combination is used for the radar system, high-end audio, I would say amplifiers, and mixed signal ICs, right? Because of this combination, silicon germanium, many foundries, many European foundries are very much dedicated towards the combination of silicon germanium. So if you are attached with some of the European counterparts, they must be very much focusing on silicon germanium. Any questions so far? If not, I'm just moving forward with the basics of PN junction diode. So this is one of the major part where we had the foundation of the modern electronics. And I know you know better than PN junction diode than me, because I have learned almost 3 years the same thing. That okay, if I need to know the semiconductor, I need to know the PN junction, and then PN junction needs to get repeated every time wherever there is a physics intersection. So what did it do? It replaced the vacuum tubes. Vacuum tubes were huge. They used to get hotter and hotter with the usage, and they used to burst like a light bulb. Now with the PN junction coming in, the vacuum tubes are completely replaced with the smaller substance, more reliable substance. It does not get heat up and blast like a tube light. It is more energy efficient, and finally the fraction of the cost. Again, I will be repeating cost at multiple levels because cost is an important factor for any of the disruptions. So if you are trying to disrupt anything, if you're trying to change anything, it will be backed by the cost. And if the cost is cheaper, then it is easy to replace. Now, it definitely replaced, but it gave a challenges in terms of the quantum effects at the nanoscale. So heat dissipation, that is the major issue. Then the leakage part, everything is leading to the change. And finally, we are now moving from atomic scale to the newer compounds, newer materials, and finally near frontiers. So, so from last so many years, we have been studying about the carbon nanotubes, different materials, as well as some of the studies are going with the waveguides, where it is emitted via light. Some of the carbon nanotubes, the conductivity is faster. So these are the new frontiers, new compounds, new materials, and these are the new innovations over the years. Now, this PN junction has definitely led to something. I mean, that something is called transistor. And that transistor also has significantly grown over the years. So I would come to the transistors. And if somebody asks me what we do, we just say we manufacture billions of transistors, or we design billions of transistors, but at a different level. So this is the evolution of the transistor. And the first one is the planar MOSFET. So 1960, from 1960, we are using the flat channel MOSFET structure until 2011, we have used this planar double gate MOSFET. There is something called SOI. This is silicon on insulator. And what we have here is there is an backgate control to you reverse bias control for the chips. Companies like Infineon, onsemi, these are the companies which uses silicon on insulator techniques, where you have a reverse bias. There is an additional voltage which is supplied so that you can control your transistor in a better way. But again, this still comes as a part of your planar MOSFET, and it is the same part of the evolution. In 2011, there came a FinFET by Intel. It was introduced at 22 nanometer, and the major reason was the leakage. Okay, now the leakage in MOSFET, the leakage was prominent. That means when you're switching from 1 to 0 or 0 to 1, there is a back current which used to flow, and this current was very heavy, and this current used to either heat up the device or generate an additional heat on top of whatever it was generating. So that was a reach. And then came the FinFET. And FinFET, what's the difference is it is ultra low leakage compared to the MOSFET. Now, I would like to I always give the analogy so it is easier to understand. So, like we have a light bulb. So, in previously we used to have a light bulb of 100 watts, or I would say 10 watts or 20 watts or 40 watts, right? Today we are having an LED light in our complete home, which is combination of 3 watts, 6 watts, 12 watts. This is the range. So we have, I mean, the leakage, or I would say you are getting the same level of illumination as your 40-watt bulb in your 12-watt LED. Now that's a change, right? And because of that, even though cost is higher, you are willing to afford LED light instead of your normal tube lights, right? Even the cost is 3x, you are using it because it is at the end of the day giving you a power savings. Again, this power saving is always on paper. Your light bill, or I would say your electricity bill, will be same or adjusted to the inflation. You will never see that difference, but still at your home, you will prefer to choose LED light over the traditional light bulb or tube light. So that's the difference between the FinFET and the MOSFET. Till 3 nanometer, FinFET is dominating the world. And because of the FinFET, you can see that there is a structure which is created. Now the gate was here. If you see the channel used to form here, and the gate was on top of it. So there is only one direction out of 4 direction. The gate has a control. When the FinFET came, it has a 3-sided control. So if you see that the channel is going inside the gate, so it has 1, 2, 3. So when you have a 3-sided of control, definitely your leakage is gonna reduce. But when your leakage is reduced, so what ideally has happened is that this geometry was horizontal. So let's say there are 100 electrons moving from this geometry. Now, in this geometry also the 100 electrons are moving, but just imagine that this has become, instead of horizontal, it has become vertical. And that has given more control. But what has happened, the channel has become thinner, and that has given to further short channel effects into the transistor. And that has led to the GAA-FET, that is a gate all around field effect transistor. Now, what is GAA-FET is nothing but you have, instead of one, you have a multiple sheets of the gates inside, multiple sheets of the channel inside your gates. So there are four I would say a fork sheet or nano sheet where the gate is surrounded on all the sides and is controlling the flow of the electrons. Now this is has started getting used on 3 nanometer, I would say 2 nanometer to be very precise, and that's where we are all right now. I would say we are started using this particular technology. And what is the future? Again, this is also not a scalable technology, I would say. We have a limitation of GAFET. So finally, there will be either CFET or there is a CNT-FET. The CFET are nothing but we were trying to stack NFET and PFET vertically. So if you see this source and drain are in the horizontal fashion, if you see, but if we are trying to move it into the vertical fashion. So this vertical, if you see this image, it's not very much clear, but there is an oxide layer, and there is a gate, and then there is a source and drain. That's how it's going to work. So we're trying to make everything vertical so that we can further shrink the transistor. And I will come to the point why we are shrinking the transistor, why it is more and more useful. You will understand a little bit later in the upcoming slides. So FinFET has a limitation on the parasitic capacitance and the cornering effect. And that's the reason where we have moved to the GAFET, and GAFET has a similar challenges, and that's where we are moving to the CFET. Now, wrapping up the transistor, whatever we have discussed so far, again, you know overall transistor better than me, but this is a complete cycle where each and every invention is captured, each and every breakthrough is captured, right? Each and every milestone is captured till 2022, where we have just manufactured GAA transistor, and that was first demonstrated by Samsung. So I'm not going through all of that because it's a visual as well as a written communication. Once you have the slides, you will see each and every innovation, or even I have taken all the slides from the Google itself. And again, for each and every slides, there will be a logo from where I have used the slides. So this particular slides belong to the KLA. KLA is one of the prominent company in electronics and manufacturing. I'll cover those further into the detail. Any questions so far, or I should move forward? Because I am not able to see any of the raised hands. So, ma'am, any questions? If there is a silence, I just move forward. Okay. So the front end is basically called a fab, or I would say a fabrication unit. And the one which is coming near Dholera. And I will also discuss why so far we have not manufactured any of the fabs, and we have not participated in any of the semiconductor manufacturing activities. But yes, the fab needs a clean rooms, and there is something called EUV machines you might have heard of. And there's a rise of a company which is called ASML. And there are so many funny, I would say, images which are also going with respect to the ASML, because if tomorrow something happens to ASML, and we will be doomed. The semiconductor industry will be doomed if the ASML plans to shut off tomorrow. Then we'll work on the manufacturing floor, discuss on the manufacturing floor, and finally the yield management. So this is purely part of the fabrication process where the chip is actually coming, and this is not part of the VLSI design flow. Okay, so this is a part of the information, but this is a very well part of, you can cover it into the academics, as well as these are the opportunities which are there at front of our doors. So clean rooms, this is how the clean rooms looks like, and the ISO standard 2, that's 100 ppm is what is required for the clean room. And you can see that the person who is operating this clean room wears a bunny suit. And this bunny suit is, you need to remove all your clothes, and then you need to sterilize yourself. You need to go through a 3-layer of sterilization process. That means you have a minimal clothes on, and they will sterilize you. And then you move to the bunny suit room, then where you will wear your bunny suit. And in this bunny suit, you can see that this person has a naked eye. This is also not allowed. You will be only some of the rooms have naked eyes, but otherwise you will have a spectacles on. Now, this is how the classic fabrication unit will look like. There will be multiple set and host of machines which will be doing, and this machine will be operating in pure play of vacuum. On top of that, if you see here, there are some of the overhead running lines, right? So these are the lines where most of your wafers get moved on, because I have personally witnessed one of the foundry unit of Intel back then, and these carries kind of autonomous robots which will carry your wafers, and that they will transit wafer from one station to another station. So the human intervention in fab, they try to make it to the as minimal as possible. So this is the part of the clean room. And again, analogy is important. Since you are based out of India, you know that in India also there are a couple of companies, or I would say medical companies, who manufacture our medicines. And to manufacture our medicines that we eat, right? Some of the famous medicines are Dolo 650. For any of the pain, doctor prescribed Dolo 650. But you need to know that the clean room to manufacture Dolo 650 is here, ISO 7. Whereas to manufacture your chip in your mobile phone, it needs ISO 2. So this is the difference between how many particles of the impurities are present in your medication versus how many impurities are present in chip of your phone. And that's where your phone is working and you are working as well. But I hope this analogy is clear that Zydus Cadila versus TSMC. So we have many Zydus Cadilas in India. We have so many medicine manufacturing companies, but we do not have a TSMC in India. Lithography machine. Now, if I take a little bit of time here, and this is how the lithography machine looks like, and this is just the open heart of the lithography machine. Again, it's very difficult to see inside the lithography machine, but this is how, I mean, this lithography machine will cost in the range of 350 US million dollars. One machine. It takes 1.5 years just to manufacture or just to assemble and manufacture this machine to ASML. ASML, if you give an order to ASML that I want this machine tomorrow, they will say, no, I don't have it. You will need to wait for 2 years and then you will get this machine. And this machine gets shipped to a company or to a location by 4 cargo flights. 4 cargo flights. That's how big this machine is. And the important part out of everything are two important parts. One is lens and illuminator, and another one is EUV source. First of all, I'll talk about lens and illuminator, and then I'll talk about the source. But before that, I'll go a little back into the history. So where we started with the optical lithography, and the wavelength of the optical lithography was 365 to 430 nanometer. And that's where the chip fabrication and lithography started. After that one, we came with the direct UV, and optical lithography was very successful until 90 nanometer of the technology. After 90 nanometer technology, it was very difficult to reduce or shrink the transistor with the optical lithography. So there came a direct UV lithography. In direct UV lithography, the wavelength was 193 nanometer, and we were able to reduce the transistor size, and we were able to reduce the transistor size till 28 nanometer. And from 28 nanometer, we started struggling. So what did we do? We definitely find a workaround. We are engineers, and we know how to go beyond the system, and we know how to break the rules. And it's always fun to break the rules. And somebody comes up with the idea, hey, there is no polish to catch today in that signal, and I'm okay to not to wear a helmet, and everybody would be happy to break that rule and move forward. So that's where direct UV, we had struggled beyond 28 nanometer, but there comes something called double patterning or quadruple patterning, which made it possible to manufacture chips till 7 nanometer before going to the extreme UV. So once the direct UV hits the limitation, there came the extreme UV. And extreme UV, we were able to get the wavelength of 13.5 nanometer. You can see the drastic change between the direct UV and extreme UV. Now, the extreme UV is combination of multiple parameters, which I'm going to discuss. But this 13.5 nanometer wavelength is able to manufacture a device or the geometry as small as 8 nanometer. And when it is able to devise this geometry, it is able to manufacture the high end of the chips, which are working at the 2 nanometer. Now I'll come to the calculation how the 2 nanometer or 8 nanometer comes in the picture, but a little bit of basics over here. Now, what made a difference? So just for 5 years, there was a company who was just trying to make a mirror. And that's a surprise, right? That mirror, they were not able to make. So to reflect the light, there needs a mirror, and that mirror assembly, we have something called numerical aperture of a lens or of a mirror, and everybody was using 0.33 numerical aperture during the direct UV. So there is a company called Zeiss. You are having some of you might have lenses of Zeiss, and you must have heard in your phone that there is a Zeiss camera, or if you have heard of Sony, Sony cameras uses Zeiss lens. So this Zeiss company has manufactured 0.55 numerical aperture mirror, which used to reflect the light, and this mirror took almost 5 to 6 years to manufacture that particular mirror, or how to come to that mirror. It took so much of innovation, and then this we were using different droplets for the EUV, but then we are using a tin droplets at very high temperature, which are then fired to get to print the smallest dimension using this particular lens. So this combination of tin droplets as well as lens, or I would say a numerical highly focused lens, we are able to come to the something called extreme UV. And again, coming to the cost, yes, it's costing around $350 million. If you want this particular machine, you can buy it. Okay, now coming to the fabrication flow. There are 5 major steps, and if you go a little bit deeper into these 5 steps, there are almost 13 to 14 steps. So this machine, whatever you see here, this machine is capable of doing multiple things along with couple of patterns, which are the steps which are mentioned here. So deposition, nothing but growing a thin layer of materials on the wafer. So let's say if you are trying to paint on a canvas, so if you're just putting a whitewash on a canvas, that means you're just putting depositing something on the canvas. So even if your home is getting painted, you just put a whitewash in your home. So that's what is called deposition. Then something is called a photoresist. And there are so many fun facts about the photoresist, but yeah, photoresist is a kind of a material which is a light sensitive material, and you apply that particular photoresist directly on the wafer. Now, before lithography, before lithography and after photoresist, there is a something called mask. And lithography is nothing but it just prints the pattern. It just, it will draw the pattern on this light sensitive material, which will be used for the printing of the chips or manufacturing the chips. Now, this mask will block the lithography where it needs to print, so that when using the edge, or it's kind of a removal process where your lithography is not there, those areas will be removed, and that will help to do the complete chip. Okay, so the etch is removal of the material where your lithography is not done. Okay, and it's like a mask. So if you must have seen somebody printing a logo of a company by a spray mask, then you have a shape of that company, and wherever there is a shape, you will spray the paint, and then that name is already written. So similarly, lithography is nothing but the spray of the paint on the photoresist, but there will be a mask which will be blocked, and that mask, so the spray will be in the rest of the area, the mask will be intact. And then what will happen? Then there is something called etching. Etching is the removal of the materials from the areas of the mask where there was a mask, so that you can create a geometry on top of one another. So chip is nothing but a multi-storied building of an apartment which is being used, but it has first of all process of spraying and then removing, spraying and then removing, spraying and then removing. And on top of it, there are other important in between steps called ion implantation, which is called doping. So if you want to change the property of the silicon at the regular interval of time, You just try to pour some of the things on the silicon to go ahead and change the properties and adhere to what we are looking for. So this is how the complete process looks like. I'll take a break of a minute. I'll take a water and come back, sip of water. So please allow 2 minutes of a break. Ma'am, in between time, if anybody has a question, can we gather some of the questions? Yeah, please. Okay. Coming back to the complete fabrication steps. So first we get a complete ingot of the pure crystalline silicon. And this ingot is very big and it is sliced into thin wafers. This wafer goes for the polishing and then happens for the deposition. That means a spraying of the material. Then the photoresist. We just ensure that the photoresist is of a pure thinnest form and it is very, very uniform. The lithography is done and then the print is developed through the etching. So lithography is on the complete chip, which happens in the mask, the area where it is not, lithography is not done. There the mask is there. Once the mask is removed, the etching is done. After the etching, the iron implantation is done, and then again a removal steps happens. The resist is removed, and then this complete cycle goes through multiple rounds. So in traditional 2 nanometer design, here it is written 4 to 100 times. In 2 nanometer design, this complete cycle is almost 200 times. So the number of cycle increases, the number of cost of your chip increases, and that is a costly affair. And once this is done, then you have a complete set of chips on your wafer. So let's say your wafer might have a 500 chips. And then that chip is kind of sliced. It's simple like we are slicing a round cake into a pieces. Same way the chips are sliced and then again packed and assembled and then send it to the end users. But these chips will be tested at multiple stages, which I will be covering in the upcoming slides. Now, apart from that, I'd just like to take some of the important steps, and this will help you to understand the complete ecosystem. How does the ecosystem works, and which are the elements? I mean, we have not left a single element on the earth to get to the semiconductor manufacturing. So starting from the noble gases to the materials to the compounds to the assets, we are using everything and anything, right? I'm just covered the high level, but if you take a complete periodic table, semiconductor process is using a complete periodic table as such, and all the possible combination. So major gases are helium, neon, argon, krypton, xenon, radon, and oxygen. So these are the major gases which are used in the fabrication process. If you know one of the prominent or highest supplier of xenon gas is Ukraine, and Ukraine has one of the edge on the semiconductor. If this was stopped, then there is a huge challenges. Similar to gases, we have metals, and once you know that metals, gold, copper, platinum, palladium, ruthenium, tungsten, titanium, and many more. So these, all the metals, if they are rising the prices in the market, you know where they are heavily being used. And each and every material is being used for the semiconductor process. And the acids. And H2SO4, H2O2, NH4OH, hydrogen fluoride, HCl, H3PO4, and finally H2O. H2 is not an acid, but it's in water. So I have not written here, but sulfuric acid to hydrochloric acid to phosphoric acid, each and every acid are being used, and these acids are being used in the purest of the purest form. Whatever we use at the commercial grade is very, very cheap, but these are 99.999% pure, or they are using up to 7 decimal to test that the purity of the gases or acids. That's the requirement of the fabrication technology. Now, I will come to the yield management, and then I'll cover the companies as well. So, what is yield? And yield is like the fully functional chips versus the total chips that are manufactured. So, if you have a 300 wafer and you are trying to develop a one particular chip, then out of, let's say, the capacity of that chip, the wafer is 500 chip, or let's say your dimension of the chip is such that you are able to manufacture 500 chips. Sorry, I'll just correct this particular part. So if your chip is X by X dimension, and then for a 300 wafer, you are coming to 500. And out of 500, the number of fully functional chips versus the total chips is called the yield. Now, if I have a 10% yield for 500 chips, that means only 50 chips are good, called something called non-good dies. So there is a concept of KGD. It's called a non-good dies, and these non-good dies are like whatever are fully 100% functional as well as hitting the full performance. That's what is called a fully functional chips, and these chips should function after the packaging. I'll come to the point how that there's a difference between die and there's a difference between chip. So this difference is very much important. So what is yield? Yield is the number of good chips that I'm having it. So if I have 50% of yield, and let's say I have 500 chips per wafer, then I only have 250 good chips. Now, the 3 nanometer wafer will cost around $20,000, one single wafer, and only I will be able to manufacture 500 chips. Apple is selling millions of phones, so you can see how many chips they will need. And this, if I take, then it is directly reflecting the cost. So I will have an $80 per chip. Now, if I have an 80 per chip, then your iPhone price is, if the traditional iPhone price is $800, it cannot afford one single chip of 80. So it needs to go to the yield of 90%. So that if the chip price is 40 or 50, then it is viable to have a complete iPhone to be sold at, $800. Now, all the companies or the foundries try to achieve 90% yield for any of the process. Otherwise, it is very, very expensive for foundry. It is very, very expensive for the customer. Okay. Both foundry as well as customer will not be happy, and they try to achieve this to give a complete and lesser amount of cost. Now, coming to a little bit more analogy in terms of the 3 nanometer versus 2 nanometer. So let's say if you're, what is the shrinking of the technology? And until you understand that, it is very difficult to visualize. So let's say 3 nanometer will have, you're able to make 500 chips, but in 2 nanometer, you will be able to make 700 chips per wafer. So the number of wafers, so this price per chip will gonna come down, because in your 2 nanometer, even it will cost $21,000 for a particular wafer, but my overall cost per chip will reduce because I am having a 90% of the yield. And out of 700, can you please mute? Sorry. So to have around, out of 700, or let's say 750, you are having a very good number of dies, and those dies will be useful, will be bringing your per chip price down. Okay, so this is what is important, not this one. What is the cost per chip? And companies are trying to do whatever they can to bring this particular value down. Now, there is something called binning, right? 50% yield means there are 250 good chips, but that does not mean there are 250 bad chips and that needs to be thrown away. So there is something called binning. So there are minor defects. Let's say your frequency is your processor is running at 4 gigahertz. It is designed to run at the 4 gigahertz, but out of 500, only 250 are running at 4 gigahertz. But out of rest of the 250, 100 are running at 3 gigahertz. So this 300, the 3 gigahertz processors are called binning, and these will be used for the low-end application. So, or I would say bifurcation in terms of different names. So what they will do is the company will produce the same phone. They will label the same phone. This is my phone, and this particular phone is costing me around 1 lakh rupees. But I have another phone, which is a variant of this phone, but is using a different chip, but it is costing me 70,000 rupees. So this difference is called binning. And when you see a same chip in two different products having a two different price, that means you need to understand that the binning has been used and your chip performance is not as good as your high-end performance. So that's what the binning comes into. Like if you see that iPhone also manufactures something called iPhone CE, which is a different variant of the same chip, but at a different cost. And the reason for that is binning. Now, as a cross reference, I would give a factory outlet of the shoe. So you must know that there are Nike factory outlets or Skechers factory outlets across all over India. Now, what are this factory outlet? It's nothing but there are minor defects which are not visible to us, and you are getting the same shoes which was 10,000, but in factory outlet, this shoes is on discount, and we are getting this particular shoes around 7,000 rupees or 6,000 rupees. But these defects are not very major, but these are already thrown out of the quality assurance test. And that's where these factory outlets work, and you get a better discount. So similarly, instead of discounts, you get the discounts in terms of the product, not the chip. The chip discount will be to the original company. Now, these are just a very high level snapshot of all the companies and the domain. I have written a country's name. Now, why I have written country name? Because this is where the geopolitical stress are happening. You have a dominant, only one single player dominant in Europe. There is no other company. So if this company shuts off, or if Europe comes tomorrow saying that you need to stop export to the China or Japan, you know what will happen to the system. So any of this company will get stopped, and you will have a counter effect. Now, out of everything, there is one more company which is similar to ASML, and that is in Japan. I'm sure everybody must have heard of Ajinomoto, right? Ajinomoto is heavily used in food, okay? But you might not know that there is a compound of something called Ajinomoto buildup film. It's called ABF. And without ABF, your chip is not possible. And it has a market share of 95% in all the chips in the world. So Ajinomoto is a one single company which rules the insulators over the substrates. And that's the exactly Ajinomoto is ideally a company name. And that particular company creates a film. And that film is used for the semiconductor manufacturing or as an insulator material. And the complete world, the complete chain of the semiconductor is again dependent on that. So each and every company, there are very very, very less competition, and they are very good in the niche compounds or niche elements or niche market that they are working on. So that's how a complete the system is, or complete game is. Coming to the packaging and testing, I'll just cover on the packaging of the systems, the concept of KGDs, which we discussed previously, and then the new frontiers and new systems moving from SOC to SOP, board to a package. That's where we are moving. But I'll also cover on in terms of the foundry ones before going to that. So why India did not had a foundry called TSMC or SMIC or anything so far? So the first of all, TSMC consumes 77% electricity uh, of Taiwan, and it is projected to take 12% of the electricity. Now, if you install the plant TSMC plant in any of the state in India, it will consume electricity equivalent to one single state in India. Even as of today, there are so many villages in India where there are no electricity. So providing such a humongous electricity to a company is very, very difficult. That's number one. The second number is water. The amount of water is again an equivalent to state, which needs to a foundry. And this water is ultra pure water. The amount of water for a foundry is 10 million gallons per day. And this water is used heavily inside the foundry. And then after usage of this water, you need to look at the waste management of that water as well. There are so many chemicals which are mixed with that. Now, on top of this particular part, all the foundries of the world generate around 15 million metric ton of CO2. That's a combination of almost 30% of global PFC. That's perfluorocarbon, which is resultant of the greenhouse gases. So the amount of pollution which this foundry releases into the air is very, very high. So the combined effect of setting up a foundry is very, very expensive to the locality as well as to the available resources as well. We do not have that level of resources so far, and we do not have that level of ultra pure water to supply to the foundry because it consumes equivalent to a state. So either you feed it to the people or you give it to a company. One is you need to choose one, and definitely so far we have chosen one because so now we are able to generate electricity in terms of the requirement that we have. Just a key on that. Testing of the dies. I previously I told that there is a difference between die and the chip. So die is something which is before the packaging when there is a wafer, and any the die is fabricated on top of the wafer. Okay. So once the complete wafer is manufactured, and that particular wafer has, let's say, 500 dies, or 500 chips, let's say 500 dies are working, then it will translate to 500 chips. So what will happen before the wafer is cut? Each die is tested then and there itself. So the testing, the direct complete testing of the wafer is done. And once that testing is done, then whichever are good dies, only those die are cut. Rest of the die will be left as is. So let's say there are 3 dies in together which are not working in a row, then they will only cut the rest of the dies and they will leave these 3 dies. They will not try to even cut because that's an extra cost because machine is consuming so much of electricity. So once the dead dies are gone, then this dies are sliced from the wafer, and once again they are tested individually and sorted according to the binning. That's where the binning comes. Here, whatever the testing will happen will ensure that your die is working at the desired frequency voltage or it's working at the lesser frequency and voltage. And that's where the binning happens, and it's segregated into a different part. Once that binning is done, then it is going for the packaging. There is a different slide on the packaging as well. And once that the packaging is done, Then there is the again a testing happens on the package, and then chip goes through something called a burning, right? So once the die, the process from the die to the burning is like die, then it will go to the lead frame. The lead frame is nothing but the metal structure that supports the die and to the solder pads, which is inside the package. You can see once the lead frame is completed, then you will go to the underfill. Underfill is something called the epoxy that will protect the solder bumps. And then something called encapsulation. Encapsulation is a layer of epoxy resin on top of that. And then finally, a burn-in will happen. And this burn-in is nothing but testing of the chip at high voltage and temperature. If chip got blasted or burned or anything, or over voltage also applies to the chip, and if it does not work, then it is thrown away. Otherwise, after this burning, the chip is actually comes to the board and then it is soldered into the board or shipped to the end users. So this is the flow of a company called Amcor, and that's this where how the testing and the final packaging happens after the die is cut. So you can see that this is the wafer, right? And it is divided into the chips. Once this is divided into the chips, it is something called comes to the um, die attach, and this die attach is nothing called but a lead frame, right? The lead frame is a wire bond structure, and then it goes to the wire bond. So lead frame happens, and then it goes to the wire bond. And once the wire bond is completed, it again goes through the testing. At each and every stages, the testing happens. Here is something called optical testing. That if let's say during the wire bond process, your wire A was supposed to touch to the pad A, but somehow it is touched to the pad B instead of pad A, and that's a problem that gets caught into the optical correction. So once that is done, again it goes to the mold. Mold is nothing but the encapsulation, that is a molding of the package. Once the molding is done and the complete package is done, then once again it goes to the testing. And after testing is done, let's say if any of the component is done, then again it will go through the laser marking machine. So laser marking is nothing but if you look at the chip, it has written that Intel Core i3 processor. That's the laser marking machine, and that's what happens finally. So this complete process happens after the testing of non-good dies, and again after each and everything, the chip is tested and then sent to the final round. Coming to the advanced packaging, this is what is happening as we speak today and from last couple of years. We are moving from a single chip to the system on package. So system on chip is moving towards system on package. So what we used to happen is previously we used to have on board we used to have a chip which is a processor. On processor, next to the processor, we used to have an LPDDR4, that is a memory, and these two were connected by board, and then over the board there were copper lines which were drawn, and that's how it used to conduct. And that's where we used to have a complete product, or let's say the working chip or working board that we call as of today. Now this complete system is moving inside one single package, so that you don't have to have multiple chips on the board, but it will be inside one single package. So what are this kind of packages? So one is a 2.5D system. That means the SoC, that is a processor, and HBM. HBM is nothing but the high bandwidth memory. These both are on a single package. So the latency between your processor and memory reduces. That means you get a faster operation. That means your processing time is faster, and whatever the output you are trying to do will be faster. From 2.5D system, because it's a side by side, we call it a 2.5D system. 3D system is a two SoCs stacked via TSV. That means that there is a one single plane, or let's say you can think of an apartment. or I would say a duplex apartment, right? Previously, we used to have a 4 BHK home on a single floor, but the land is becoming costlier. So instead of 2,000 square feet area having a four single bedroom land, we are moving to 1,000 square feet area, but we are having a 2 rooms above and a 2 rooms below, and that means we are saving of the area. The land cost is increasing. Similarly, the chip cost is increasing, right? So the lesser number of chips, the better, and that's where they are trying to make it a sandwich system, and that's a 3D system. Then the new part is chiplets, right? So similar to SoC and HBM, that is processor and memory, what they're trying to do is they're trying to divide the chip into multiple small fragments. Now again, remember the 500 number. So for a single wafer, you are able to manufacture, if there is a very big chip, you are able to manufacture 500 numbers. But think of this terms. Let's say you are dividing that chip into 5 different parts. 5 different parts. That means your single chip, single wafer is able to manufacture 2,500 of small dies. And now we are trying to join this die on the package. So what happens is your overall cost will reduce in terms of the chip manufacturing, but you are just putting that on a single package. That is something called a chiplet. And finally, a 3.5D system. So this 3.5D system is nothing but a humongous system of 2.53 3D and the chiplets. And this is what we are calling a heterogeneous packaging, or we are moving towards a complete system system on package or SOP kind of a model. And this is nothing but a simple snapshot. So if you just remember, this is a processor, just your iPhone processor or Qualcomm processor or i5 processor of Intel. These are the processor, and as of today, these are individually available. Now this is a 2.5D system where the memory is on the side and processor is here, and we are completely encapsulating into one single package. So you will get only one single package saying that the product name is XYZ. So this we are moving from here to interconnect bridges. That means this is the triplet system, and this is ultra high density RDL. Again, these are more of jargons, and silicon stacking. This is what a 3D system is called, and this is something called system on wafer or wafer on wafer. This is again a foundry terminology which are being used for stacking of multiple chips on top of each other. And finally, co-package optics. So this is where we are heading towards. This is 2026 and beyond. We are testing a couple of things into this particular domain, but we are trying to get a breakthrough. The combination of silicon and the photonics is what is the future for even higher mobility or higher transport. Okay. So, okay, I think there is a lot of information that is going through your head, but I'll just try to quickly cover a couple of things. Now, this is a complete ecosystem, or I would say this is still a partial ecosystem. This is not a complete ecosystem. And where we are working, or I would specifically say where all the companies are working, or more of the industry, or where we would like to focus, at least at the India level, is this much. Okay, these are equipment and packaging and testing. These are definitely there in India. If you what is happening in Gujarat, the Micron plant which is coming, this is part of a testing, packaging, and assembly. That's the Micron that has established plant in Gujarat. Also in northeast in Assam, there's another company which is planting a similar testing. Can you please mute yourself? Yeah. Okay. But this is where we need to train our engineers. We need to bring the system. So fabless chip pumps, these are very well active in India. That's where we need to focus. Foundries are also active in India. There are so many foundry units are there, but the foundry work is not happening. The manufacturing is not happening, but designing is still done in India as well. Non-chip firms from recent years, the last 5, 7 years, all these software companies where they have big money in the pocket, they have started demonstrating their own chips. Apple is making their own chip, Google is, Microsoft, everybody is making their own chips. IP design and software. So yeah, intellectual property is one of the major part, and that's where everybody is protecting intellectual property. So these companies have an IP, like I was talking about ARM. ARM is the world #1 IP provider, and their IPs are, CPUs, GPUs, DSP IPs, multiple IPs, and then comes the design software. Like apart from everything, I mean, all the design centers are there. You cannot design without the set of these companies. So there are three major companies, Synopsys, Siemens, and Cadence. They provide an ANSYS as well, but ANSYS is now acquired by Synopsys. So all this company provides a software or design software, you can say CAD tools, to design all the chips, and then this chips goes to the manufacturing part. These are called IDMs. I would say they have their own design centers as well as foundries, so they don't need to go out. So all these companies have their own foundries. They are, I would say, stand alone to manufacture their own chip without help of any of the outside system. Like the fabless company needs to depend on foundry, but this does not need to depend on the foundry as such. So that's what is complete semiconductor ecosystem, but I would request that you can focus here in this set of system and train the engineers in their respective direction. Coming to the VLSI domain, so out of complete flow, right? We are just here, VLSI domain, and next couple of days you will go through this particular into a very brief, very technical details as such. We have multiple speakers lined up for that. So I will just cover in a nutshell. First one is the system architect, and there are multiple domains on top of each and every domain. So let's say if I call a system architect, there are 4 different or 5 different kind of expertise is needed. So there will be a 5 different skills are required for the system architect. There are 4 different skills required for the RTL design and verification. There are 4 different skills required for the sign off. So that means 4 different engineers who will be working here, knowing 4 different things than each other, right? So system architect is the first one where they design the system, they design the SoC, and they decide the performance of the product, and that's where the complete heart lies. They are the architects. Like it's a blueprint similar to our building architect. These are the system architect. Then comes the RTL design and verification. Again, whatever the domains I'm covering in terms of the engineering use also. So RTL design and verification means they will code the RTL based on the specs which are given. Once the coding is done, there will be another engineer who will be simulating. On top of when the simulation is done, there will be another engineer who will be prototyping, and after that, there will be another engineer who will be emulating. So during the RTL design and verification, and continuously hand in hand, there will be a DFT and test which will be ongoing. So these are the pre-silicon testing which happens along with that. So these are all are interconnected. It's not a one single unit, or I would say these are not one individual single steps. All the steps are interconnected steps. uh, DFT and tests. So there will be pre-silicon and post-silicon. This all the functions will happen hand in hand. And then there is a physical design. I'm part of the physical design domain, so I know a complete physical design. So synthesis, place and route, time enclosure, and PPA. Again, there will be a different set of engineers who will be working here. And then comes the sign off. Again, ECO, there is something called engineering change in order. Like if you have forgotten something, you need to redo something, that's called an ECO. If your complete design is completed, then there is something called timing sign off, physical sign off, formal verification, and EMIR verification. These are also an important steps. And then there is a packaging and designing. So once your die is completed, then you need to do the package design as well. The design of the package is also not easy. It needs to go through a thermal testing, a different set of mechanical testing to ensure that it is not burned, it is not hot, or it is not, getting blasted. All those things needs to be taken care in the package design as well. And all of complete thing that definitely needs an automation. Automation is important, so there will be a certain engineers who will be working on who will be developing AI tools, who will be developing flows and methodologies for this complete system. So if I talk about a complete system, there will be minimum 25 different expertise which will be there. So you can have a different set of expertise, different set of engineers for each and everything, right? So if somebody is entering into the VLSI domain and if you are guiding them, you can say there are 25 different branches within the VLSI domain itself, or they can choose out of 25 different set of things, right? So that's the vast of VLSI domain. And again, we have not talked about fabrication domain, testing domain. That's a completely separate. This is a purely a chip designing part which I'm talking about. Moving to 2026 and beyond. So what will happen after 2026 is done. So at, finally, we will be moving to advanced packaging, and that's where we will be scaling our Moore's law. So Moore's law have reached to a very stringent limit of expansion, and that limit is in terms of the miniature form of the ICs. So we are we are struggling to move beyond 2 nanometer, 1.4 nanometer. We have a limited growth. So what we are trying to do is like take an example of a city like Mumbai. So Mumbai has limited growth, and now the land is not there enough. So what people are doing, they're trying to go vertical so that you can accommodate more number of people. That the similar situation happening in all the metro cities like Bangalore, Delhi, and everything. Similarly, we are moving towards advanced packaging so that we can pack so many compute within a single package. So we have something called 20 by 20 die, and this 20 by 20 die previously used to have only one single processor, but now this 20 by 20 die will have a processor, memory, as well as the additional processing power as well, or other peripheral units. So that's what we are trying to squeeze everything into a vertical so that there will be a minor increase in the height, but you will have a more power within the same footprint. So that's what is happening on the 3D IC. Then there is something called silicon photonics. So we are trying to bridge a silicon directly after or I would say we are trying to make something called waveguides or electrons traveling directly from the silicon to transfer the data faster. So there are multiple frontiers. In fact, there are colleges in Hyderabad. I think it's very advanced in silicon photonics. As an academics, you will know better than me. But this is another frontier where we are moving. You should not be surprised that tomorrow there are so many new things will be coming on the silicon photonics. And finally, heterogeneous packaging. So there will be some more advances in terms of the packaging parts, right? So 3D IC, we are right now at the helm of the 3D IC, but heterogeneous packaging is nothing but the combination of the 3D IC and the silicon photonics. So that also combined will be a future. So this is what is 2026 and beyond. And definitely there is a huge scope, and the next 10 years, if I can say, belongs to this particular stream of a specific stream in the VLSI domain. What else? Quantum computing. This is a very different frontier. Again, since you are part of the academics, you need to know the peripherals of what is happening other than, semiconductors. That's a quantum. So three major part: qubits. Something is dependent on superposition theory, that is having multiple states at the same time, 0 and 1 at the same time. And then, the fundamental of entanglements. So you can have entanglement means you can have two variation at the same time, but it should be correlated so that you can take a decision. And finally, the interference. That means it will try to amplify the correct answers and cancel the wrong ones. That's what is quantum all about? Again, I am not at all expert in the quantum computing, but definitely this is an emerging frontier. Multiple companies are working towards it, and as in definitely academia, we should focus on that. So with that, I would like to discuss on the career opportunities as well. So where are the career opportunities lie? So research and development. So you have seen a complete cycle from the fabrication, from the equipments to the physical design or VLSI complete domain. So when coming to the research and development, we need scientists, we need mathematicians, we need chemists who can develop a newer and newer chemicals and pollute less and less of an environment. We need a physicist who can push the limit beyond 1 nanometer, because 1 nanometer is the distance between two atoms for the silicon. So we need all the scientists, research and development. Definitely academics is a way to go for that. The second career opportunity is engineering discipline. So electronics, computer, IT, chemical, mechanical, biochemical, and environmental. Total 7 direct engineering disciplines are affected with respect to the semiconductor industry. And definitely it's not a vice versa thing. So if you have a Tata chemical plant where you are developing a sulfuric acid, that means you are only liable for the chemical engineering or maybe mechanical engineering. But the semiconductor industry is the only single industry where you have a breadth of all the lines which are intersected in terms of each other. You need to know the computer, even the computer AI data and AI engineer is needed because he makes a software to design the chips. IT engineers are needed because they need to stop the attacks from the outside, vulnerabilities. Chemical engineers are needed for the foundry. Mechanical engineers are needed for the machines. Biochemical engineers are needed for the materials, and environmental engineers are needed to sustain the environment because foundry generates almost humongous amount of waste which needs to recycle, directly recycled. Otherwise, there will be so much of waste which is literally hazardous to the human life as well as any of the living organism. And finally, business and operations. So business and operations also we need auditors, we need marketing people, and we need sales people as well. Because without them, if you have designed everything, but you will not be able to sell anything, correct? And indirect opportunities. So if there are companies which are catering to the semiconductor domain, these are the indirect opportunities which will come. Human resource definitely will be there. Lawyers, right? Everybody is suing one another. So what's wrong in having a lawyer? So lawyers' future will be very good in at least upcoming years. Civil engineering, because without a building, engineers will not sit, or without a home, engineer will not sit. So civil engineering, designing smart cities, designing smart infrastructure, this will be needed. And then finally, a blue collar workforce. So these are the indirect opportunities which are being created uh, as in side effect of, or I would say as an after effect or before effect of a semiconductor industry. But as in direct impact, if you are a professor, lecturer in any of the domain, you can say that with the semiconductor industry, there is a direct impact for all the line, or there is a direct opportunity for all the lines. I have added some of the useful links where I have taken a content from, or where I have created content from. There are some videos which you can watch out of it so that you can get familiar with what I have been discussing so far, and at least you can correlate and take your reference from. So with this one, I would like to end my presentation. Let me know if there are any questions. I am open for the questions, as well as, yeah, please let me know the feedback as well.
Very, very, very well done, Karan.
Thank you, madam.
You took us from the histories to the future. It was a wonderful session, Karan. Anyone up with the queries?
if you have any queries in the future, please note down. I'll be happy to answer even the later stages. We have also discussed with the faculty members here that during the end of the sessions, once all the sessions are there, we'll try to collect all the speakers and try to address your queries at the end of the day as well. So if you have anything, if you remember tomorrow as well, please submit your questions to Sneha ma'am, Chami ma'am. We will answer those questions once we have it.
Thank you. It was
Yes,
very
keep.
it was very insightful session and very informative. It gives a complete landscape of the right from the semiconductor evolution to the complete manufacturing process. Thank you very much.
Thank you so much. I'm happy to.
So yeah, we have the proud alumni. We are proud of our alumni from 2012 batch, Karan. Well
Thank
done.
you so much.
So for this session as well, let us all turn on our cameras for a while, and then I'll be sending the feedback form link for this particular session. Again, today in the WhatsApp itself, from tomorrow we'll work out with the chat of Teams. Yeah. Requesting everyone to please turn on the cameras.
Ma'am, my camera is actually not working due to some technical issue.
That's fine. Yeah, so I believe everyone is fine with the session and the speed and everything that we are dealing with. If anyone has anything to be shared, can share your feedback through your email or in personalized WhatsApp message. Yeah.
Sure.
See you all
Sure.
tomorrow at 6 p.m. Putting the link of the feedback form soon in the WhatsApp. See you all tomorrow sharp at 6 p.m.
Good night,
Thank you,
Thank you
everyone.
so
everyone.
Bye.
much.
Thank you, everyone.
Good
Have a
night,
good night.
everyone.
Have a great day.
Bye bye.
Thank you.
Good
Bye.
night.
Good night,
Everyone.
everyone.
Good night.
Thank you, ma'am. Good night.
Thank you.
Thank you so much.
Thank you, ma'am.
Thank you, ma'am.
You're welcome.
Thank you.